and we and then we see it is all these kind of stuff needed for particular project. But the problem here is that we don't have any command swig here in the Windows, which makes it fail with Box2D. And we can search for swig.
So I think last time we finished discussing TD.
And then we can find versions to make it work.
Okay.
Also to
So we first discussed Monte Carlo.
compilers.
So I updated slides for lectures 9 to 11. So please go ahead and download the new version. So for Monte Carlo, Monte Carlo essentially collects episodes, and at the end of every episode, update the return. Average return is the value function for a state. So Monte Carlo can be used for policy evaluation or for control. So for policy evaluation, you simply average the returns for every state. For control, you can follow the policy iteration paradigm. So here, the generalized policy iteration for Monte Carlo looks like this. The difference with the previous policy iteration for MDP planning with known MDP is that with known MDP, you evaluate the policy for until convergence, until the error is less than the threshold. So you all the way go to the convergence for evaluation of VPI, and then move to update the policy with a greedy policy. But for Monte Carlo, you because the evaluation of policy is not until convergence. So it lies between the two extremes. For policy iteration, you always evaluate to convergence, but for policy for Monte Carlo, you evaluate to some degree, but not to convergence. And we discussed also off policy MC prediction with importance sampling. That is for so we collect trajectories with behavior policy B, but we evaluate the target policy pi. So we add this weighting factor rho to the updated equation. So with the on policy Monte Carlo, we don't have the rho. So we incrementally update the value function with the newly collected G, the return for a state T. But now we weight the G with the rho before updating VST. So if you compare these two, one is on policy, one is off policy. So the top one is on policy. So I should say on policy versus off policy. So the main difference here is so the main difference in here is this weighting factor for our policy. So you the W is updated, and when you update the return, you have gamma times W times G. Whereas for on policy, you don't have the W weighting factor because the target policy is the same as the behavior policy, so W is equal to 1 for on policy. So, and then we moved on to TD learning. So just I added this slide to compare TD versus Monte Carlo. So for on policy, the difference is Monte Carlo uses the return at every end of every episode to update the value function, whereas TD uses the one-step prediction as the target to update the value function. So TD does more frequent updates. And we discussed off-policy Monte Carlo with importance sampling by adding a weighting factor. So you can also do TD with off-policy TD with importance sampling. But the weighting factor now is the single step ratio between the policy between the target policies probability for action AT divided by the behavior policies probability for target AT. So as opposed to the cumulative ratio of the behavior and target policies from T until the end of the episode for Monte Carlo. So you can see clearly the correspondence here. So the main difference is that MC does the update at the end of every episode, so it does less frequent updates. But TD does more frequent updates. So the random walk example, so if you're given the random policy of moving left or right with equal probability, then you can calculate the value functions with analytical solution of a set of linear equations. That is, you know the MDP. So this is for known MDP. You can solve for them. But what if the MDP is unknown? As an agent, you must stumble around in the environment until you learn the value functions. So the learning process, I contrasted here TD versus Monte Carlo. So Monte Carlo can only learn at the end of each episode. So starting point is the center point, central position. Suppose it moves all the way to the right to the terminal state. And then Monte Carlo will update all the states encountered in the episode, which include states C, D, E, and their value functions are updated to be the same because we don't have a discount factor. So otherwise they will be different. So for TD, so the first time you move from C to D, the update does not change VC because the initialized values are still valid. There's no new discovery. So from D to E, it does not change VD. But from E to terminal, you get a reward of 1. So now you see something fresh. You see something that's novel. This causes an update of VE, mainly because of this a new discovery that there's a reward of 1. Plus the terminal's reward of 0 minus the original estimation of the value of E is 0.5. So now VE is 0.75 because now starting from E, it can go to a terminal and earn 1 reward. So you can see that at the end of this episode, for Monte Carlo, all 3 states value functions are updated. But for TD, only E's value is updated because TD does not have memory. So when you're at C, you update C. When you're at state D, you update D. So you must update the current state. You cannot go backwards and remember what happened. TD does not have memory. Unlike Monte Carlo, which keeps track of all the visited states, TD just goes and forgets about the past. So as a result, so it can only update VE. Because at the time of updating C and D's value functions, E has not made the transition to terminal, and the reward of 1 was not yet known. So C and D's value functions are not reflecting this future event. Only E's value function is affected by this transition from E to terminal. So episode 2, I have 3 parts. So it moves around among the positions CDE essentially. However, it never goes to the terminal. So for this episode 2, because the episode never ends. The Monte Carlo never updates anything. Monte Carlo updates only happen at the end of each episode. But TD continuously updates each state as it goes on. So for part 1, so every episode starts from the center state, C. So as it moves from C to D, the update is null. So there's no update because D's value is still 0.5. There's no change. But when you move from D to E, D sees this new value function of VE of 0.75. So that causes its value to increase. And then next, you move from D to C. No, you go into CDE and then back to DC. Notice that when you update a VE, the next state is now D. So because you're moving to the left, so TD update, the next state is always your next position, next state. So now E finds out that D's value has increased now to 0.625. So it uses D's new value to update its own value. So it's a little bit circular, right? D is updating its value based on E's value. And then when you travel to the left, E is using D's value to update its value. So this is a bootstrapping. That is you are basing your estimate of your current value function on your transition reward plus the next state's value function. So as you can imagine, suppose that this little robot just goes around and D and E forever, then eventually they'll converge to the same value because there's 0 reward for taking the transition among them. So these two states are essentially equivalent. So as it moves among these CDE states, the values are getting mixed together more and more. Eventually, uh, so based on the analytical solutions, no, that's for random policy. So D and E's values should not be the same because it has equal probability of moving left and right. So D has a half probability of moving to the right and earn 1 reward. So E has a chance of moving to the right and earning 1 reward. So E's value is higher than D. Because there's a terminal state on the left. So once you reach the terminal state on the left, the episode ends. So there's 0 reward. So the more you go, the more the closer to the left, you have the lower the value function. So A has a low value function of 0.167, and B has slightly higher, and so on. So C has an equal probability of ending on the left or on the right. So C has exactly a value of 0.5. So I think what I said before. So suppose you move between D and E forever for many times. Then this will make values of D and E equal, but that's not a random uniform random policy. So for uniform random policy, their values will not be equal because you will not move between them infinitely. You sometimes you gotta move to the right of E or to the left of D. So for that policy, their values will turn out to be different. So so TD versus Monte Carlo, TD converges faster, and having a higher learning rate alpha helps achieve a faster convergence, but has a larger fluctuations. So this is the mini grid war example. So Monte Carlo, you simply average the reward you see, average the cumulative reward you see for every state as the value for that state. Very simple algorithm. For TD, you so suppose after 4 episodes with transitions B, C, D, so transitions B and then C and then D, getting a reward of +10, then you can do the TD update. So from first from B to C, now every transition has a cost of -1, reward of -1. So it encourages the termination of the episode. So B to C, you get a -0.5, and C to D, you get a 4.5. That's the first episode. And then next episode, and now I write the update equations in a slightly different form, but it's the same exact equation. So gradually, after you repeat 4 episodes, the values seem to be converging towards some limit, but it seems to be slow. But if you have a faster learning rate, then they converge faster. So the C value of C is 9 because it can get to D with -1 reward, and D has a value of 10. So obviously, it should have a value of 9. So this is the summary of the differences between dynamic programming, which is a full backup of all the children nodes of a given node, given state, versus temporal difference learning, which is one-step sample backup, and Monte Carlo, which is multi-step sample backup. So deep backup versus shallow backup, and sample backup versus full backup. So full backup is only possible for the model when an MDP model is available. Otherwise, you can only do sample backup for model free. So here I compare MC versus TD. So TD can learn before knowing the final outcome. So it can learn online after every step. But MC must wait until end of each episode before return is known. So TD can learn without the final outcome. So it can learn from incomplete sequences, and MC can only learn from complete sequences. So incomplete really episodes. And TD works in a continuing, that is non-terminating environment, whereas MC only works for episodic environments. MC has high variance and zero bias. So the return, the target value, the return is unbiased estimate of the value function for state ST. It converges to V pi ST even with a function approximation. And it depends on many random actions, transitions towards in each episode, which can be very long with many thousands of steps. So that's why it has high variance. That is across different episodes, its variance is very large. So it affects the convergence. And it's not sensitive to an issue of value, but TD has low variance because it's a one-step estimate as opposed to many steps for Monte Carlo. It has some bias. So the target is the reward plus next state value multiplied by a discount factor gamma. It's a biased estimate of V pi. It's a bootstrapping estimate. So it's not the ground truth. Therefore, TD converges to V pi ST for tabular setting, but not always with function approximation. And Monte Carlo does not exploit the Markov property, so it may be more effective in non-Markov environments, such as a partially observed MDP. TD exploits Markov property, so it does not work well for a POMDP. So next I'll discuss SARSA and Q-learning. So TD is a model-free way to learn the value function of every state by sampling. But if you want to get the optimal policy, we need the MDP model to go from a value function to action value function Q. So the formula is this. So sum over all the next state S prime and reward to get the Q from the V. And then you can use the action selection, greedy action selection, to get the optimal policy pi. So this is greedy action selection. So SARS and Q-learning, they learn Q, the action value function, instead of the value function S for use in generalized policy iteration for control. So this makes action selection a model-free tool. So for this simple maze, one-dimensional grid example, each grid position has a value of associated with it. But because each position has two possible actions, left or right, so the Q, we have 8 Q values versus 4 V values. So if you think back to the Bellman equations, TD solves the Bellman expectation equation for state value function by sampling. So because this equation has this P R S prime S A, that's the model, the MDP model. So for model free setting, we can only evaluate this expectation with a sampling. So here, the capital S, capital R are the particular values at t plus 1 or t for state and reward. The small s and small r represents the generic variables representing the random variables. I think the conventions may be a little confusing. I think before I said capital letters are random variables and small letters are concrete variables. But in here, the small letters denote random variables, and the capital letters denote the concrete sample. So that's TD for solving the Bellman expectation equation. For the Bellman expectation equation for action value function for Q, Sarsa solves it by sampling. And you also have expected Sarsa, which also solves this middle equation by sampling. So the reason that it's by sampling is because, so you have this summation here, which is really an expectation over all next states. But you don't have this function. You don't have this P for model free case. So what happens is that you sample many runs and collect the reward and next Q, and then you update the Q by so this RT plus 1 corresponds to this R here, and the Q corresponds to this small q pi here. So the difference here is that you removed this expectation over S prime, and you removed expectation over A prime. And then this means that you're not taking expectation analytically, as in the Bellman equation. Instead, you're computing the expectation approximately by sampling. So you're sampling many rewards and many Q value functions, and because you're running many samples, eventually, on average, their value will converge to the expectation. So it's a common trick to evaluate expectation or average by sampling. So the only difference between Sarsa and expected Sarsa is you have the sum over A prime left over in here. So for Sarsa, so for Sarsa, you are using this sample to estimate this whole thing. So you're removing the sum over A prime. But for expected Sarsa, you're keeping it. So at every state, you're evaluating the expected value of the next Q. And this capital Q is only sampling the Q pi. So are you worried that this is really model? Is this really model free? It is model free because the model is this guy, P, not the pi. The pi is known. So what's unknown is the environment's behavior, environment's response to agent's action. So the agent knows it's pi. So I may choose left with 50% probability, to the right with 50% probability. So that's agent's own choice. So pi is known, the unknown part is p. So this is still model free. And finally, for Q-learning, you're solving the optimal action value function by sampling. So now you have the max left over in the sampling equation, but you removed the environment expectation. So now the Q for next state action value function is taking a max instead of taking expectation as the expected SARSA. So for the backup diagrams we saw before, so this is the Bellman expectation equation for V pi. So you're backing up from V pi S prime to V pi, and TD is just a sampling version of it. It samples a particular transition from S to S prime and does a backup update. For SARSA, notice you're backing up from Q pi S prime A prime to Q pi SA. So the little blue circle is the Q node. So in this blue circle, you are starting from the earlier state S, and you're committed to action A. And you need to estimate the value of taking action A in state S. That's the action value function. And then SARSA does this estimate. For expected SARSA, so you're taking expectation over all A prime. And for Q-learning, you're taking a max over all A prime. So also TD and SARSA are all on policy methods. That is it always so SARSA always takes the action A prime. But for expected SARSA and Q-learning, they're off policy, which means that the backup. So for Q-learning, the backup is the based on the max Q S prime A prime. But the action taken for the behavior in the behavior policy may not go to that node, Q node used for backup. So you may go to another action, a double prime, not the A prime used for backing up the update. For expected SARSA, the backup is based on expectation. So it's a blend of all the possible S prime A primes based on a probability distribution. So obviously they could be a blend of different outcomes. So it's obviously also our policy because the backup value may not correspond to any action A prime. It's just the average expectation over all possible A primes. So we had 4 Bellman equations before. Bellman optimality, we had 2 equations. Bellman expectation, we had 2 equations. But for this Bellman equation, we don't have a corresponding sampling version for it. So it's computing the V star, the optimal value function, by taking a max over all actions and taking expectation over all next state S prime. And reward plus a next optimal value function for S prime. So because of the max A in front, it's not an expectation over a distribution. So we cannot solve for V star S by sampling. Sampling only works if you have a expectation in front. So for the other, for all these 3 equations, Bellman equations, you always have a expectation over A, over S prime, over S prime, over S prime. So these can be converted into the sampling version. But if you have a max in front, you cannot do sampling-based evaluation. So for the Bellman optimality equation for action value function, you have a max inside. So this is okay because your sampling is evaluating all possible S primes. So this part is replaced by sampling. But for the inner max, you're not sampling away. You must actually examine all the possible next A primes and taking a max. And similarly for if you're not removing the sigma A prime in the expected Sarsa case, you must examine all the next A primes that take an expectation. But for Sarsa, if you remove the sum over A prime, then you simply then for Sarsa you are performing sampling-based evaluation of both the next state and the expectation over next action. So both are done by sampling. But for expected Sarsa, you're not evaluating the summation over A prime by sampling. You're only evaluating summation over S prime by sampling. But for Q-learning, for Bellman optimality equation, this part cannot be evaluated by sampling. You must actually keep the max A prime in the sampling equation. That's why for Sarsa, you have 2 versions. One is the sampling version, one is the expected Sarsa. But for Q-learning, you only have one version. This guy cannot be removed, the max. So any questions? So this slide is taken from David Silver's course. So this course is very good. I highly recommend it. So it just draws the diagrams, backup diagrams in a different way. Same content, exact same content. So for full backup, you have the Bowman expectation equation, and TD is a sample version of it. For policy evaluation, TD is a sampling version of policy evaluation of V pi. And SARSA is a sampling version of Q policy evaluation for Q pi. And Q-learning is a sampling version for the optimal value, Q value, or Q star. So exact same content as my diagram here, just drawn in a different way. And also it's missing the expected SARSA. So this just contracts SARSA with the Q-learning. So the only difference is here. One has a max, one doesn't. So because of this difference, Q-learning is off policy. So it takes a max A among all possible actions, whereas the SARSA is on policy. So yeah, if you notice, there's another difference here. So A prime used for updating Q must be taken. So it's assigned to A, which means that it must take action A. But there's no such term here, which means that the action taken may not correspond to the max action used for the Q update. So that's where the on policy versus off policy part is shown. So the SARSA must take one step and use that exact action to update its Q value. Whereas for Q-learning, it uses the max among all the possible next states. And then you can take arbitrary action, actually. Here, it chooses from epsilon greedy, but you can choose a random action, a random policy. That's fine. Because your target policy is continuously being improved during Q-learning. So your behavior policy can be some random, very adventurous policy, whereas it doesn't affect your target policy. But for SARSA, your behavior policy must be epsilon greedy or some variant. It cannot be purely random because there's only one policy. It must continuously improve as the algorithm runs. So here just shows the target policy is taking a max in every state. So, but the behavior policy may be arbitrary. So it could be, so this seems to be epsilon greedy. That is the optimal policy, and here is moving left. But here you add a small epsilon of moving right. And similarly for every other state. So the target policy is always greedy. So this argmax means greedy. Behavior policy is more exploratory. Could be random, could be epsilon greedy, or even some arbitrary policy. And there's no need for important sampling. So if you had one policy, then you need to have important sampling to account for the differences between the target policy and your actually running policy. But here we we actually have a different two different policies. So on the right, you see the suppose from state st plus 1, you have three possible actions, a prime, and one has the q value of -3, one has a 4, one has 6. So you take the max, you update the q here, update the previous q by this 6. So the other two do not matter. So expected SARSA and Q-learning are both our policy. Expected SARSA subsumes and generalizes Q-learning. So the targets, the difference is one is taking expectation over A prime, one is taking max. But if the target policy for expected SARSA is greedy with epsilon equals 0, then it's exactly Q-learning, because a greedy policy pi taking expectation over a greedy policy gives you the max. That's the definition of a greedy policy. So Q-learning is just a special case of expected SARSA. So expected SARSA improves over SARSA by eliminating variance due to the random selection of AT plus 1. So if you look at the backup diagrams, so SARSA is suppose at this point it has multiple A primes. So SARSA is evaluating the expectation over all the all the A primes by sampling, whereas expected SARSA is taking expectation over all the possible S primes. So suppose you had 100 different choices of A primes, not S primes. So and then SARSA may perform 1,000 samplings to get an accurate estimate of the expectation over all possible A primes. But expected SARSA can get that value by one single expectation evaluation. So that's why SARSA has a higher variance, whereas expected SARSA has a higher computational overhead. Yeah. And SARSA and Q-learning. So this is the exercise from the textbook. Suppose action selection is is greedy with epsilon equals 0. Is Q-learning exactly the same algorithm as SARSA? Will they make exactly the same action selections and weight updates? Answer is no, because SARSA chooses the next action A prime in S prime based on current policy and updates the Q function, whereas Q-learning first updates the Q function based on max of next Q, and then chooses the next action A prime in S prime in the next iteration, so derived from the updated Q function. So if you look back in the pseudocode for salsa versus Q-learning, so for Q-learning, it updates the Q and then chooses the action from the updated Q. For salsa, it chooses an action, A prime, using the old Q, and then updates to the new Q, and then commits the action based on the old Q. So even if they're both using greedy policy, not epsilon greedy, there's still this subtle difference. So if you don't think carefully, they look the same, but actually the Q update happens at different times. Of course, if epsilon is not 0, they're obviously different because for the Q update, Q learning always uses the max, the greedy policies Q, whereas for salsa, this Q here may be non-greedy due to epsilon greedy. So if epsilon is 0, then these two are the same. However, the update and action selection still are a little bit different, as I explained here. So the salsa chooses the action before updating the queue, whereas Q-learning updates the queue and then chooses the next action. So here's an example for TD, salsa, and Q-learning. So MDP with 3 states and 2 actions at each state with no discount for simplicity. Terminal state is T. So from D, you can either go to take action at 1 and with reward minus 100 and go to T, or take action 2 with reward plus 4 and go to T. So in this example, I only use the lower branch for simplicity. So suppose you have n episodes of B, action 2, reward 0, D, and action 1, reward minus 100. So if you're wondering where the name salsa comes from, it comes from state action, reward, state action, salsa, S-A-R-S-A. So that's a salsa right here. So episode 1, the VB. So that's the TD. First, we look at TD for value function. So VB is 0 because all the value functions are initialized to 0. So VB does not change, but VD is updated to minus 10 because of the transition with a minus 100 reward. Episode 2, this value, updated value, yeah, I think I should highlight it to show that it's updated. So the minus 10 is used to update the VB. And the VD is now updated to be minus 19, which is in turn used to update the VB, and so on. So you can see this minus 100 reward gradually propagates backwards. Initially, it only affects VD, but next, it gradually goes back to VB. And if there's any earlier states, and goes back there. So at time infinity, if you have infinite number of such episodes, B to D to T, and then you can, these two eventually converge to minus 100, because D makes D has a minus 100 reward and goes to T, so its value will eventually converge to minus 100, and B will gradually be affected by D, because the reward for transition from B to D is 0, so it should also have the same reward value function as D. Now, what if you have a bunch of episodes of B action 2 0 and D action 2 4 reward? Then VD is first updated to be 0.4 because of the plus 4 reward, and then this will affect B's value, and then D's value is updated to be 0.76, which will affect B's value even more. So eventually they'll both converge to 4. So for SARSA, I think that's just my scratch thing. So for SARSA, now the table is larger. So instead of VB and VD, you have VB1, VB2 for 2 different actions, and for state B, and VD1 and VD2. So for the first update, VB2 is not changed, but VD1 is changed, and this value affects QD1 is changed. This value will propagate and affect QB2. And the next iteration, the minus 19, will affect QB2. So because in this bunch of n episodes, you only take B action 2, D action 1, so only these 2 columns are affected. So you never take action 1 in state B and never take action 2 in state D. So these 2 Qs are still their original value of 0. So, but QB2 and QD1 are updated. And eventually they will converge to minus 100. So what if you have a Q-learning? So the difference here, so QD is not affected. QD1 is not affected by whether it's Q-learning or not. But QB2 is affected. So QD1 is updated to be -10, and QB2 is affected by should be affected by the -10. However, it's masked by the max operator. So this -10 is blocked, it's masked by the max operator. So QB2 is not affected by this -10 because it takes the max over all the actions available in the next state D, and you see that one. Wait, did I make a mistake? QG 0 max of Q. All right. So because if you look at the two Q for D, QD2 is never changed because it's taking a max over actions, which is a null set because the terminal state. Yeah, I should really. So this is the terminal state with no further actions. Terminal state has no actions. Therefore, a Qt A is 0, and QD Q learnings wait episodes Q learning. Okay, QD1 okay, that's the different episode. This is the one. Okay. For this episode, because every time D takes the action 1, it gets a reward of -100. So only QD1 is updated to be non-zero. QD2 stays 0 always. So QB2, based on the equation here, you're taking a max over actions 1 and 2. That is max of QD1 and QD2, which is 0. So the any updates by QD1 is ignored. So the when you're evaluating a QB2, you know you are going to state D. In state D, you have two possible actions, and you know that one of them is very bad. So you simply ignore that bad option, ignore that bad action. So what if you take the B2, D2, these two transitions for Sarsa, QD2? So D is always the same. D is not affected by either Sarsa or Q-learning, but B is affected. So QB2 is gradually being pulled by QD2 towards 4, towards a convergence value of 4. Whereas for Q-learning, now now, because it's taking the action 2 in state D, and it's gradually increasing QD2, and now QD2 is affecting QB2 because .76. So now this 0.4 is affecting QB because the max over 2 actions in D now picks up the 0.4 and ignores that 0. And when QD2 is updated to 0.76, the max here for QB2 picks up that 0.76. So now both Q values are pulled towards 4. So this example clearly shows the difference between SARSA and Q-learning. So first look at TD for value function. So if you have lots of transitions from D to T, it drives a VD to minus 100, which then in turn drives VD to minus 100. If you have always a transition from D with action 2 with reward 4, then these will drive VD and VB to 4. The final values VB, VD depend on the relative execution frequencies of the two transitions. So for example, epsilon greedy or some other policy. For SARSA, this D action 1 drives QD1 to minus 100, and which in turn drives QB2 to minus 100. In contrast, for Q-learning, QD1 still goes to minus 100, but it does not affect QB2 due to the max operator. So Q-learning is smarter, so it sees that that's a bad action, so it ignores that. So and then if you had a bunch of transitions with QD2 converging to 4, and then for SARSA, it'll drive QB2 to 4, and same for Q-learning. So QD1 is the QD2 is the max term. So that'll drive that'll drive QB2 towards 4. So here we assume the upper transition B to C is not taken. Otherwise, we need to account for more cases. But if you imagine epsilon greedy policy for SARSA and Q-learning, so SARSA, so I should say something more here. So If SARSA uses epsilon greedy, avoid this action 2, similar to Q-learning. So our example here is actually not very realistic, because we are saying that we are taking this D1 transition, action 1 in state D forever. So that's not realistic. So if you have epsilon greedy policy, it'll learn to avoid action 1 in state D. So eventually it'll learn the same policy as Q-learning. But this example is just to illustrate the policy evaluation part, not policy, not control. Yeah.
Sorry, Songwai.
Yeah.
I guess you mean it avoids action 1 in state D, not action 2.
Avoids action 1. Tries to always take action 2. Yeah.
Yeah, you have written avoid action 2.
Avoid action 1. Sorry. Yeah. Our example here it illustrates the policy evaluation, not control, for some fixed policy. Okay, so that's Q-learning and SARSA. So we have this example of cliff walking. So reward is -1 on all transitions except those into the region marked the cliff. Stepping into the cliff incurs a reward of -100 and sends the agent back to the start. So SARSA will learn the safe path, whereas Q-learning will learn the dangerous path, which is optimal because it's shorter. But because occasionally it falls into the cliff because of the epsilon greedy action selection. So SARSA takes the action selection into account because it's an on-policy algorithm, so it learns the safer but longer path through the upper part of the grid. So during the episodes, SARSA will have a higher sum of rewards during the online learning, SARSA has a higher average reward. However, if you gradually reduce epsilon to 0, approaching a greedy policy, then both methods will converge asymptotically to the optimal policy. So if epsilon is 0, then the lower path is indeed optimal because you never fall into the cliff. Well, this is assuming a deterministic environment. If the environment is not stochastic, then still Q-learning may this lower policy may not be very good. Yeah, this is environment is deterministic. Yeah, only action selection is stochastic. So this is textbook's chapter 8, planning and scheduling. So so the model we talked about model based and model free. What is the model exactly? So one type of model is sample models. So it produces just one of possible outcomes sampled according to the probabilities. It can approximate probability of each outcome, requires a little memory, or distribution models, which produces the complete probability description of all possible outcomes. Probability distribution. So it can compute exact probability of each expected outcome and requires more memory for storage. So here, this is describing the possible outcomes for 2 coin flips. So either model can be used for state space planning, dynamic programming approaches, such as value iteration and policy iteration. So when we discussed MDP before, we were discussing the distribution models, but sample models are also fine. So for random sample, so for the Q planning, so the planning uses simulated imagined experience generated by a model, and learning uses real experience generated by the environment. They can be combined. Agents uses planning to learn that moving right and falling off the cliff is bad. So it avoids the moving right action without actually doing it. So you are performing the actions, and based on a Q-learning or SARSA or expected SARSA, you are doing one update after every action. But with Q planning, you are thinking in your head. The agent is thinking silently without taking any action. What if I take an action here? What will happen? What if I take action there? So it's performing this planning in its head. So this one-step tabular Q planning assumes first you have this sample model, this kind of sample model. Assuming you have this model, and then you send this state action to the model and get a next reward and sample next state. And then you apply this Q-learning update. Notice that this particular A is an imagined action. not an actual action. So this is Dyna algorithm, which unifies the direct Q-learning with direct RL with real experiences. And then has indirect RL, that is model learning followed by Q planning. So real experience is used to improve the model to make it more accurately match the real environment, and which is then used for planning. So model learning. So the difference from the Q-learning is the red part. The other part is the same as Q-learning. So the actual steps are to do a model learning. So assumes a deterministic environment after every transition. It records in this table entry for ST80 the prediction that RT plus 1, ST plus 1 will deterministically follow. If the model is queried with a state action pair that has been experienced before, it simply does a table lookup and returns the last observed next state and next word as its prediction. So that's the model, a simple table lookup. And during planning, the Q planning algorithm randomly samples from state action pairs that has previously been experienced. So real experience builds a model and uses simulated experience to plan updates. And on the other hand, for direct IR update, you learn from real experience as before. So you have two update branches for the same value function. So here's an example of this maze environment. So the agent initially has a random policy, and it stumbles around until it reaches the goal. Afterwards, only this one state policy is updated, its Q value is updated. The other Q values all stay 0. So all the experience before reaching G is discarded in normal Q learning. But for DynaQ, it keeps track all the previously visited states and actions and rewards and learns a model by keeping track of them. So and makes it makes better use of environment interactions. So for future episodes, for Q learning, this Q will gradually propagate back. So the next episode, when it ends here, it'll update this guy. The next episode, it will update this guy. So the propagation of Q is really very slow. But for Dyna, it uses the learned model to plan better policies for all previously visited states. So by the end of third episode, a complete optimal policy has been found. So the N here, N 50, N here is the number of planning steps within the Q planning. So here's the example with N equals 100. So in the first episode, it takes 184 actions for the agent to reach the end goal by a random policy. And then in the next, before you take the next action, 184, and to the 185th action, you do 100 steps of planning in the middle. And the planning will update these two Q values although the agent is just moved from here to here, so that's the actual action. But in its head, it's doing simulations and performing Q planning based on learned models. So it updated these two Q values. Despite that, it has never moved close to these two positions. And at action 187, there's two more actions taken. So it moved here and here. But 2 steps, there are 200 more planned steps. So it learned more Q values by planning and so on. So even though the agent is still moving around in this corner, it never left this corner, the policies are being improved. The Q values which determine the policy are being improved by the planning steps over here. So that's the DINA algorithm to combine planning with learning to make better use of past experiences. And for prioritized sweeping, this is so in the original DINA algorithm, we say that we randomly choose previously observed state and action and do Q-learning based on that. But that's not a very good strategy because obviously, if you're performing Q updates over here, over here, over here, they're not going to help you much because the changed values are over here. So only these have non-zero Q values. So you should prioritize the states close to this goal state and nearby states. So by prioritizing the state action pair prioritized by the size of the change. So that's the insert with this guy. Priority is determined by the size of the expected change, and then pop out the highest priority in the queue to preferentially update these entries. So for the maze example, you work backward from the goal state by giving higher priority to states leading to the goal state than those far away from it. That is, you try to prioritize these states over these states. So based on prioritized sweeping, you can get more efficient learning. So what if your model is inaccurate? So what if suddenly there's an obstacle arriving in the middle during your learning? It's okay. So the models may be incorrect because the environment is stochastic and or a limited number of samples have been observed, or because we are using function approximation, or the environment has just changed. So then the planning process will compute a suboptimal policy based on previously learned incorrect model. But when you actually encounter this obstacle in the real experience, the error will be corrected. So DynaQ Plus essentially adds exploration bonus to encourage exploration. So it adds this kappa square root tau. Tau is the number of the transition has not been tried in tau. So so the longer a transition has not been tried, the more likely that it's stale and may be out of date. So it may have changed. So by adding this exploration bonus, it preferentially explores the transitions that have not been visited for a long time. So here, in the reward, we add additional exploration bonus. And with the DynaQ Plus, the cumulative reward, so this environment suddenly changes as time step 1,000. Originally, the optimal path is here. After the change, the optimal path is here. It's like this. So so Dyna and DynaQ Plus will realize this. So there's a flat area where this is perhaps actions that has not encountered the differences. The differences lie in two positions, this position and this position. So if your movement, your actions have not encountered one of these two positions, then it's not going to learn, but eventually you'll learn these two positions. And DynaQ Plus performs better. So this is, if you recall from the what's the multi-armed bandit example, where you had exploration bonus for the arm that you haven't pulled for a long time. So this is similar to encourage you to explore the unknown. So this is a summary of the tabular methods. So if you have a model, then we use the MDP planning methods, policy iteration, value iteration. But if we don't have a model, then we either learn a model first by doing Dyna or Q planning, or we do completely model free. And if we can do a learn per episode on the right with Monte Carlo methods. Monte Carlo can either do evaluation only or do control to improve the policy. Or if it's if we want to learn per time step, then we use SARSA or TD or Q learning. So, and then TD can only be used for policy evaluation, not control, because it evaluates the V, not Q, and you cannot go from V to Q without a model. Whereas SARSA and Q learning, they learn the Q directly, so you can use them to get the greedy policy by argmax. So any questions on this value-based IR? So I actually have two more lectures. One is on function approximation. One is on policy-based IR. So I think I'll keep going, perhaps for some time. And let me let me set the exam scope to be lectures 1 to 10. So lecture 11 will not be covered by the exam. I will finish lecture 10 and 11 today, but you can leave after lecture 10. And the lecture 11 is only for your entertainment. Okay, so let's take a break for 10 minutes and come back at 4:50. Also, if you want to leave now, you can always watch the video. Okay.